Welcome. In this video, we start 3.8 Implicit Differentiation. We'll take 2 days in this section, and today we look at what is implicit differentiation, and we tackle some basic problems. Let's begin. So, some curves in the plane are implicitly defined curves. Here's a classic example. X squared plus y squared equals 9. That's the circle centered at the origin of radius 3. And on this circle, there are points, many points, and if I take any point on that curve, x, y, it's some pair of actual real numbers, x and y. And those numbers for x and those numbers for y satisfy the equation x squared plus y squared equals 9. That's what the curve is. The curve is the set of all points whose x coordinates and y coordinate satisfy x squared plus y squared equals 9. What makes it implicit is that I can't solve for one of the variables. I can't solve for y by itself, and I can't solve for x by itself. The x and the y remain inextricably linked together. Here's another example. This one is an ellipse with a slightly different, slightly more interesting equation. So different equations will produce different curves in the plane, and every point on the curve is an xy pair where the two coordinates satisfy that equation. We'll just take a look at a few more implicitly defined curves. Sort of a gallery of implicitly defined curves. This is interesting, the one on the right. Since sine is periodic, you get a somewhat periodic figure there. Here's the solution set for sine of x plus y equals x cosine y minus 1/2. It's kind of amazing, right? Every point on this curve has coordinates that satisfy that equation, and only the points on the curves satisfy that equation. Here's one involving E. Alright, so with these curves, we might still want to do some calculus. We might still want to know something about slopes. For example, take a look at the curve here. This is given by the equation y cubed plus x squared y squared equals y plus 1. So all the points in the plane that satisfy that equation, that's what they look like. And our goal is to figure out what is dy dx at the point 1, 1. So look at the graph at 1, 1. There's a slope through there, right? There's some tangent line that I could draw. And by asking what is dy dx, I'm really asking what is the slope? What is the slope of that tangent line through that point? Maybe I'll first address this. How do we actually even know that the curve really passes through the point 1, 1? Well, we have to make sure that the point 1, 1 satisfies the equation. In other words, if I plug in 1 for x and 1 for y, it makes the equation into a true statement. So let's see. At 1, 1, what happens? I get 1 cubed plus 1 squared times 1 squared equals 1 plus 1. Is that true? Oh yeah, on the left I have 2, on the right it's 2. Yes, that is a true statement, so the point 1, 1 satisfies the equation, so the point 1, 1 lies on the curve. Before we figure out the slope of that tangent line, we need to do a little bit of warm-up. Suppose y is a function of x. So in the back of your mind, maybe think y equals, I don't know, the square root of x cubed plus x. There we go, y is a function of x. Or y equals 99x to the 100 minus 3x. There's another example, y is a function of x. But I don't really know what y is exactly. I just know that generally y is some function of x. If that's all I know, can I compute the derivative with respect to x of y to the 5th? Kind of. This is really the chain rule, where the outside function is x to the 5th, and the inside function is the y. So I take the derivative of the outside, I get 5y to the 4th, and then I need to multiply times the derivative of the inside. Well, the inside is just y, so the derivative of the inside is dy dx. That's all I can do is to express that derivative symbolically. How about the one to the right? The outside function is sine, the inside function is y. So I take the derivative of the outside, leave the inside unchanged, and then multiply times the derivative of the inside, dy dx. On the bottom left, the outside function is just e, you can say e to the x. I take the derivative of the outside, I get e, but the inside stays unchanged, it's still e to the y. Then multiply times the derivative of the inside, dy dx. And how about this last one? Can you figure it out before I do? There we go. 1 over twice the square root of y times dy dx. But now, let's imagine that we mix in some x's. What if I have both x's and y's appearing in the expression that I'm differentiating? The trick is to remember that when you see that little dx on the bottom, that x is my variable, and y is some function in x. So, if I take the derivative, first of all, this is a product rule. This is x to the 4 times y to the 8. So, there's my u and v. I need to do the product rule. U prime times v. So 4x cubed times, and then y to the 8. I take the derivative of the first, but I don't take the derivative of the second, plus the first, x to the 4, times the derivative of the second. And now, when I come to take the derivative of y to the 8, this is where I need my implicit differentiation. It's this idea that even though I have a y there, I'm differentiating with respect to x. And so we get 8y to the 7 times, now the derivative of the inside, dy dx. So I think of that as my u prime v plus u v prime. Let's go to the right. What's the derivative with respect to x of x times y? So the derivative of x is just 1, so I get 1 there. And then the second stays the same. Again, this is the product rule, plus the first, x, times the derivative of the second. Well, what's the derivative of y? Oh, well, that's just the derivative of y, dy dx. There it is. So more simply, we could just write y plus x dy dx. We don't need that 1 in front. All right, moving down to the left, how about the derivative of x times the sine of y? Again, another product rule. So the derivative of the first, 1, times the second, plus the first times the derivative of the second. So the derivative of sine of y. So this is a chain rule. Take the derivative of the outside, I get cosine, the inside stays unchanged, times the derivative of the inside. There's my dy dx right there. Okay, how about this one? The derivative of x to the 4 plus y to the 8 plus y. Do you see what this will be before I do it? 4x cubed plus 8y to the 7 dy dx plus dy dx. Sometimes people wonder with the x, why don't I put an extra dy dx on the end of that or something like that? I suppose really this is 4x cubed dx dx, but dx over dx is just 1, so we don't bother writing that, and we end up just with 4x cubed. And the last one on the bottom, what do we end up with here? So the outside function is e to the something, so the derivative of that just stays e to the something. But now I need to multiply times the derivative of xy. And I'm taking my derivative with respect to x. Oh, that's exactly what I had up on the top right. So my solution previously will work perfectly here. Y plus x dy dx. This might take some time to play with and to understand, so I encourage you, if things are a little bit unclear, pause the video, look through these examples, and see if you can work out what's really going on. X is the variable, and y is representing some function in x. And I'm taking my derivative with respect to x, the variable. All right, we are now ready to tackle our original problem. How do I find the slope of the tangent line through the point 1, 1? The first trick is to differentiate both sides of the equation with respect to x. So both sides of this equation, they have some x's, they have some y's, but I'll treat x as my variable, differentiate both sides with respect to x. And what I end up with is, well, this, let's see, this y cubed, that derivative is just 3y squared dy dx. The x squared y squared, this becomes this whole stuff in parentheses because I have to use the product rule. And what's going on the right? The derivative of y is dy dx, but the derivative of 1 is just 0, so that disappears. All right, I took the derivative of both sides with respect to x. Now what? Solve for dy dx. This is where the algebra begins. Let's take every term that has a factor of dy dx and put it to the left of the equal sign, and every term that does not have a factor of dy dx, I'm going to put it on the right of the equals sign. So 2xy squared does not have a dy dx, so I will put that over to the right. But this term, dy dx, I'll drag that over to the left. So we should end up with 3y squared dy dx plus, and I'll just neaten up that a little bit, we'll call that 2x squared y dy dx minus dy dx. So that's what I get from pulling over that term on the right to the left. And now, oh yeah, this 2xy squared, that got put onto the right side, so now it's a negative. Negative 2x y squared. Now that all of my terms with dy dx in them are on the left, I can factor out dy dx. So 3y squared plus 2x squared y minus 1 dy dx equals negative 2x y squared. Finally, now that I've factored out the dy dx, I can divide both sides by that stuff in parentheses, and I can solve for dy dx. So it's negative 2x y squared all over all that stuff. 3y squared plus 2x squared y minus 1. There we have it. So here it is typed up neatly. Dy dx is this expression on the right. You know what? This is going to tell me the slope for any point on that curve. Any xy pair that is a point that lies on that curve, I can take those coordinates and plug it into that expression, and that will tell me the slope of the tangent line through that point. So in particular, I'm interested in the point 1, 1. Let's evaluate this at the point 1, 1. So dy dx evaluated at 1, 1 equals, well, what happens with the top? When I plug in 1 for x and 1 for y, I just end up with negative 2 on top. And then in the denominator, it's 3 plus 2 minus 1. So that's negative 2 over 4, which is negative 1/2. And does that seem reasonable looking at the picture? I think so. If I put a point at 1, 1, draw my tangent line, it's believable. It has a slope of negative 1/2. Sure. Let me tell you about a different way of solving this problem that sometimes is computationally easier. So the same problem, but we'll do a different method of solving it. The solution, method 2. It begins the same way. Differentiate both sides with respect to x. There it is, still somewhat complicated, but now I can avoid a lot of algebra if I plug in x equals 1 and y equals 1 now. At this point, what happens if I plug in x equals 1 and y equals 1? Then this whole thing becomes 3, so I have 3 dy dx plus, that just becomes 2, plus now at 1, 1, that becomes 2 dy dx equals dy dx. And now I can still solve for dy dx, but I don't have to drag around a whole bunch of variables with me. And now when I solve for dy dx, we'll just find right away the answer will be negative 1/2. So there it is. One last slide. Another example. Find the slope of the curve through the point 1, 0. And below we have the equation that defines the curve. All right, pause and try. Give this a try. So take a few minutes, go through the calculations, and when you are ready, start the video again to check your work. Go to it. And we're back. Let's give this thing a try. Step number 1, differentiate both sides of that equation with respect to x. So I get 2y dy dx plus dy dx equals, now the right side is easy, that's just our regular differentiation, 3x squared minus 2x. Let's solve for dy dx. Every term with dy dx is already on the left anyway, so 2y plus 1 dy dx equals 3x squared minus 2x. Divide both sides by 2y plus 1. dy dx equals 3x squared minus 2x, all divided by 2y plus 1. And now I can evaluate at the point 1, 0. dy dx evaluated at 1, 0. When x is 1, that numerator becomes 1. And when y is 0, that denominator just becomes 1. That equals 1. Does that seem reasonable? I think that seems reasonable. That's a slope of 1 going right through the point tangent to the curve. All right, so we've introduced implicit differentiation today. I kind of like this. You get some really cool looking curves when you get curves that are implicitly defined, and we can still use the tools of calculus to find slopes of tangent lines at various points on the curves. All right, that wraps up our treatment for today.